Hi everyone, welcome back to our channel. Today we are going to do the practical experimentation on maximum power transfer theorem. This is the practical setup required to verify maximum power transfer theorem. Coming to the circuit diagram. So this is the circuit diagram of maximum power transfer theorem. So here we have the source and here we have an 500 ohm resistor and ammeter in series connected to an variable resistance. The formula for maximum power, okay. So what is the maximum power that will be delivered is P maximum is equal to open circuit voltage square divided by 4R Thevenin. So at this maximum power, the condition is Thevenin's resistance is equal to load resistance. Whenever Thevenin's resistance is equal to load resistance, then maximum power will be transferred. This is what we need to prove here. So this is the experimental setup we are having. So coming to the circuit diagram. So this is the circuit diagram. Okay. So here we have a 500 ohm resistor and you have to connect the ammeter and you have to connect the rheostat. Now let us try to give the connections. So first one, connect the positive of the regulated power supply to the starting of the board and negative of the RPS to the negative of the board. Just very simple, just give the input and now we have to connect the ammeter. So after 500 ohm ammeter, connect to the positive terminal of the ammeter. Okay. So next, the negative terminal of the ammeter. Okay. So from the negative terminal of the ammeter, or you can directly connect here from the negative terminal of the ammeter, connect to the rheostat input. So this is nothing but the rheostat input and the output of the rheostat. So the output of the rheostat join into the negative, then it forms an closed path. I repeat the connections again, very simple. So 500 ohm resistor, ammeter and rheostat are connected in series. So just I am giving an input supply and output of the resistance is connected to the ammeter. Okay, output of the ammeter is connected to the rheostat input. Output of the rheostat is connected to the negative, which forms an closed path, and we need to measure the voltage across the resistance, which is nothing but the rheostat. Okay, so this is 1350 resistance. This is the base is the input and this is the output. Here we had given the input, therefore the complete coil will travel and it will take the output, therefore length is greater. Now the position of resistance is maximum. Okay, then current will be minimum. Now let us try to connect the voltmeter in parallel to the supply. Okay, so here you are going to get, so now current is leaving, therefore this we have to connect to negative and this terminal we have to connect to positive. So this is all about the connections of the regulated power supply and board as well as the ammeter. Okay. Now what is the procedure is, initially keep the ammeter in minimum and voltage also in minimum and just give the supply. As soon as you give the supply, first adjust the current knob to maximum position. Whenever the current knob is in maximum position, slowly increase the voltage. So the voltage what you have to apply is nothing but 30 volts. This is 28. This is nothing but 30 volts. So we have been applied 30 volts. Now here you can see here resistance is in maximum and current is in minimum. Now let's try to adjust the rheostat. So you can cross check and then you can take further readings. So now we are bringing the resistance from maximum to minimum and you can see here the current starts flowing. Okay, so this is how the procedure of doing the experiment. So now you can see here we had given the 30 volts supply through the RPS and connected to the ammeter, and now rheostat is in so maximum resistance position, that's why current is minimum and voltage is maximum. Slowly hold the rheostat and slightly adjust. So you can take current as an reference. So when you take current as an reference, you can see here, so you can take for 5 ampere, 10 ampere. Okay, so let's try to do it for multiple currents. So now 5, 10, 15, 20. So at 20 amperes you write down the corresponding voltage. So some loose contact is there, that is why it is creating an disturbance. So from 25 milliamperes corresponding voltage is 18 volts, and 26 milliamperes corresponding voltage is 15 volts, and at 30 amperes you have an 14 volts. Similarly, while you take the readings, you record it in an graph. Okay. First one is output voltage and the current for each 2 amperes of increment of current, and similarly if you calculate VL by IL, then you can get the resistance. So now we are doing at a current of 30 milliamperes initially, 30 milliamperes, voltage is 15 volts. Now let us try to proceed with another magnitude of current. So similarly now it is 32 and corresponding voltage is see here, as current increases voltage will decrease. Okay. So now it is 32 and corresponding voltage you write down. So next one you go for 35 milliamperes current and voltage is 12 volts, and next one 36 milliamperes of current, corresponding voltage is 11 volts, and next 38 milliamperes corresponding voltage is 10 volts, and similarly you can keep for 40 milliamperes current and voltage is 9 volts, and similarly 42 milliamperes voltage is 8 volts. Similarly 45 maximum, you can see here I am making it as short circuit. As soon as I make it to minimum resistance, voltage is 0, current is maximum. When if you plot it, so after plotting don't keep it for a longer time. Why? Because we had already shorted, and bring to the original portion, just keep some sort of resistance. So you try to tabulate all this in a tabular column. So when you do the tabular column and just multiply the power, the formula for power is IL square RL. So this is the maximum we have obtained, 32 milliamperes. The maximum current is 32 milliamperes, and for the corresponding voltage of 14.8 we had got a power of 471. This is called maximum power delivered from the Thevenin's theorem. The formula for maximum power through Thevenin's theorem is VOC whole square divided by 4 into R Thevenin. This you can calculate from the theoretical calculation. So this is the maximum power. When you plot the graph, okay, so this is the maximum power we obtained as 471. So from this graph try to draw an vertical line, then it will get intersect. So this is nothing but x axis is load resistance, y axis is power. So what is the value of the load resistance? Here you have been obtained is 400 ohms. Okay. So here the value of RL you obtained is 0.46 kilo ohm. We multiply with 1000. So this is nothing but 460 ohms is RL. So our RL is equal to 460 ohms. That is the Thevenin's resistance also will be equal to 460 ohms. Then the maximum power will transfer. So how to understand means, when you draw the graph of RL versus PL, so slowly with the increase of resistance, load resistance, power also will slowly increase and it reaches a maximum point, and further if you increase the resistance also the power will decrease. That's why this is called maximum power. That's why this theorem is called maximum power transfer theorem. You can see here slowly the power increases and the power decreases. Okay, this power is nothing but the maximum power transferred from source to load. This kind of circuits are generally useful for DC communication system or for ECE communication system. So where they require only maximum amount of power to be transferred from source to load. So this is nothing but the source terminal and this is nothing but the load terminal. So the maximum power will be transferred whenever this load resistance value of 460 is equal to source resistance value, then maximum power is transferred. This is the procedure of practical solving the maximum power transfer theorem. Hope you are able to understand. The theoretical calculation will be leave in the card. You can see in the card and you can do the theoretical calculation for this maximum power transfer theorem. Thank you for watching. We will meet in the another video.